Hello, everyone. Thank you for inviting me to this conference. And the topic for today's discussion is, do embryos self-correct? Now, when we talk of developmental timelines, classical embryology teaching, whether it's in mouse, humans, or any other species, has told us that embryo undergoes a very defined timeline of development, where if the day of fertilization is considered as day zero, day one has to be 2 cells, day two has to be 4 cells, day three has to be 8 cells, so on and so forth. And by day five, all the embryos have to become a blastocyst ready to hatch. And this defined timeline has been the classical paradigm in developmental biology. But do these embryos deviate from this timeline? The answer is, of course, yes. As embryologists, you all have seen that there are multiple evidences where the embryos have skipped cleavages, they have reverse cleavage, there are fragmentations, and these are defined as developmentally incompetent embryos. And based on this, the idea of Gardner's grading or morphokinetics or AI tools have evolved, where the idea is that such embryos, being developmentally incompetent, should not lead to a successful pregnancy and therefore should be excluded from transfer. However, when we look at published evidences, what do we see? Of course, grade AA embryos have a good implantation potential and a good live birth rate, but even grade CC embryos, which are typically something which we discard, about 22% of them do implant and about 13% of them do result in a live birth. And this is the data published in 2020 in Fertility Sterility in a smaller group of embryos, but a very large data set was published recently where more than 10,000 women had undergone more than 10,000 ETs, and it was shown that if we compare good grade blastocysts versus low grade blastocysts, yes, the overall live birth rate is relatively lower, but there is a good chance of a live birth rate, which is about 13%. It was earlier believed that these abnormal embryos, which looked abnormal to begin with, might have adverse pregnancy outcomes, but the adverse pregnancy outcomes were not significantly different in pregnancies conceived with good grade blastocysts or low grade blastocysts. And therefore, this led to the idea, the question that why do a proportion of low grade blastocysts even implant? Ideally, they should not implant because they're developmentally incompetent, and why there are no adverse perinatal, no major adverse perinatal outcomes. And is this because of a possibility of self-correction? The idea of self-correction got fueled in further when it was observed that nearly 40 to 60% of human embryos were abnormal, and yet we do get live birth. And studies in PGTA did show that almost 67% of human embryos to begin with are aneuploid, and if we segregate them by day three versus day five, we do see that 77% of day three embryos are aneuploid, which reduces to 58% when they reach day five. And this led to the initial idea that there should be some amount of genetic self-correction happening where the aneuploid embryos do become aneuploid, you do become euploid. However, if these euploid embryos are transferred, studies have shown that majority will result in a miscarriage and not really, and the live birth rates were very low, but at least 1 to 2% of aneuploid embryos do result in live birth. The biggest turning point came with this correspondence published in New England Journal of Medicine in 2015, where they reported transfer of mosaic embryos. What are mosaic embryos? Some cells are normal, some cells are genetically abnormal. And when such mosaic embryos were transferred earlier, it is believed that these are non-transferable. We should not give them patients because they are all aneuploid. But this group reported transfer of 18 mosaic embryos, and they resulted in 6 pregnancies with a normal karyotype. People thought that the resulting babies also would be aneuploid or normal, but these were all normal karyotype and with the 6 live births. Fueled with this idea and these observations, a series of studies eventually got reported, and the largest study of nearly 2,000 mosaic transfers resulted in 488 live births, resulting in a live birth of 24% as opposed to 33% with euploid transfers. This is summarized in a recent systematic review published in JARC, which also did show that mosaic embryos would result in a 41% live birth rate, whereas a euploid embryo would result in 49%, telling us that mosaic embryos retain roughly about 85% of the live birth potential of the euploid embryos. So why these mosaic embryos should result in live births, which are karyotypically normal? It is therefore believed that these mosaic embryos, the normal or the abnormal cells somehow are undergo a process of self-correction, and this and the embryo proper is resulting from this corrected cells, and therefore it is resulting in live birth. And this is where the whole concept of self-correction came. And the question that we are going to ask is, are the abnormal cells or the aneuploid embryos undergo self-correction? And on a more broader context, in the clinical context, we're asking the question, why healthy babies arise from poor quality or chromosomally abnormal embryos? But before we go ahead and dwell along the idea of self-correction, let's define it. Self-correction is the ability of a pre-implantation embryo to recover from developmental incompetence despite deviation from normal development. So the idea here is that the morphological, developmental, or genetic incompetence are corrected during the course of development, resulting in a normal live birth. So what are the evidences for these once considered abnormal and non-viable embryo has resolved these errors to leading to a live birth? And it is believed, and the lines of evidences are exclusion of cells at compaction, selective overgrowth of cells, extrusion of selective blastomeres, selective lineage segregation, selective death of abnormal cells, and extrusion of the unwanted or the extra DNA, which would all result in live birth of a mosaic embryo. And therefore, now the paradigm is changing, that not every early abnormality is terminally lethal. There's a possibility that many of them are corrected over the course of time. And how are these corrections? First one is reset structural integrity. You all would have seen in embryological practice that while most embryos compact very well, in some instances the cells, several cells are excluded, one or two cells, fragments generally excluded, or one or two cells are excluded when the compaction is occurring, and the rest of the compact embryo forms a blastocyst, and these excluded cells are left behind. And it is believed that these are abnormal cells which are unwanted, and the embryo is now completely healthy, made up of healthy, possibly euploid cells. In developmental biology, developmental selection has been a classical hypothesis for embryonic self-correction, where it is believed that initially a few abnormal cells are there, but these abnormal cells do not participate in any of the lineage formation. They're excluded from lineage segregation, and therefore the resulting embryo is normal, whereas despite having initially poorly functional blastomeres. Lineage choices. The embryo appears to be making active decisions of where the normal and abnormal cells to go. And in this example, when mitotic errors occur, the embryo is usually to begin with diploid, but during the course of development, mitotic errors occur, resulting in some of the abnormal cells, resulting in a mosaic blastocyst. But these abnormal cells are then restricted to the trophectodermal lineage, which forms the placenta, but the baby born is healthy and euploid, and this is called as confined placental mosaicism with a healthy live birth outcome. If the aneuploidy is meiotic origin, most of the cells are trisomic to begin with, but during the course of development, some of the cells decided to exclude this abnormal chromosome, resulting in diploid cells at a certain stage, and these diploid cells eventually form most of the lineages of the inner cell mass, resulting in a normal embryo, while the trophectodermal lineage was largely made up of the abnormal cells, resulting in placental aneuploidy, but not the fetal aneuploidy. Although these are rare events, but these are documented evidences in literature. The other evidence is selective growth of euploid over aneuploid cells. To begin with, it is believed that the good proportion of early embryonic cells are aneuploid, which we already have seen, but over a period of time, the normal euploid cells will have a growth advantage and the numbers will increase and the abnormal cell numbers will decrease, resulting in a selective overgrowth of euploid cells, resulting in a predominantly euploid embryo. Corollary, it is believed that the leftover aneuploid cells eventually are eliminated by apoptosis, and we have already spoken about special allocation and lineage contribution biases. At some point, it is also believed that the blastomere extrusion is also mechanisms of self-correction. Unwanted blastocysts, many of you would have seen in your embryologic practice, are thrown out even before the embryo is hatched. And these are all unwanted cells which are given out. And these unwanted cells which are given out, which you can also see in a live movie here, the normal cells are given out are abnormal, and people have tested these cells and they're found to be genetically aneuploid, and it is believed that the rest of the embryo should be euploid, and therefore this is one of the mechanism of early self corrections. It's not just at the level of cellular corrections, it is also there is now accumulating evidence that during the course of cell division in the earlier embryonic development, there is some amount of DNA extrusion. These are static images of live cell embryos taken at several time intervals up to 50 minutes, and it is seen here that during the course of cell division, some amount of budding happens at the tip of the nucleus and some amount of DNA is just excluded out. And you can see the same in the live cell imaging here, where at the beginning of the cell division, a portion of the DNA is released out as a micronucleus or a fragment. The cell divides and the fragment is retained in the cytoplasm, whereas the rest of the cells just keep growing, and this fragment does not form to the embryo proper, indicating that the unwanted DNA, the extra DNA, is thrown out. And this is very nicely documented in this live movie at Nicholas Placha's lab, which I'll show you right now. Let me take you to his website. And here you see a cell division. This is one cell, one nucleus in a cell, and you can see that the mitosis has happened and one of the fragment is left behind. This is nucleus of early developing embryos, and you can see mitosis happened and one of the DNA fragment is left behind. This could be a lagging chromosome resulting in a mitotic error, but this could be also an extra chromosome within the nucleus, and this extra chromosome was excluded out of the cells and the rest of the nuclei are diploid, resulting in a complete diploid embryo. So these are all possible mechanisms by which cell divisions control embryonic self-corrections. So to summarize, the proposed mechanisms are cellular apoptosis, blastomere extrusion, TE segregation, and chromosomal level rescue. However, if we look at the quality of these evidences, blastomere extrusion and compaction selection have direct observational evidences and multinucleation recovery. I'm sure I don't have to convince you all of this, that these are the three strongest observational mechanisms which are proposed for self-correction. DNA extrusion, although the data is accumulating, but studies from at least Nicholas Placha's lab have shown that even if it is occurring as a rare event, not very, very common, and the idea of true chromosomal repair has the weakest evidences. There are not enough strong evidences to support these theories. However, if I summarize these evidences, I'm sure all of you will agree to me that these are mechanisms of eliminating abnormal cells rather than repairing them. So, do the embryos really self-correct, Ploidy? I think this is a point of debate, because what we really don't know, what we have is associative evidences that we transferred mosaic embryos, we got a live birth, means some self-correction occurred here. There is a caveat to it, and the caveat is that the way we are testing these embryos through the PGTA has a strong limitation of technical noise. We know with our own experiences as well that there are issues at the laboratory during the time of biopsies if errors have occurred. If there was a difficult to do biopsies, we know DNA fragments there. Many of these contribute to noise resulting in a mosaic embryos. And there is also evidences that the laboratory which does genetic testing can also contribute to this noise. So how much of this is noise versus true biology is something which we cannot discriminate. And at this point, we do not know which are true positives of mosaic versus what proportion of them are false positives. So until we learn to differentiate between these evidences, I don't think we can strongly comment on the process of self-correction, but I think we must learn to differentiate between embryos fixing itself and our failure to accurately diagnose it using a single time point. I think errors do happen in the embryo during the course of early development. Some of the cells just die, abnormal cells simply die, and the rest of the embryonic growth just progresses normally. And where these cells cannot die or this correction has not been able to be possible, the embryos with such condition will undergo arrest and not lead to a development. So I think we should not look at whether they repair or don't repair, but I suggest we should look at how embryos are resilient. Do they have a good resilience capacity? And this resilience is the one which is going to define its ability to implant or not implant. And specifically in the lens of mosaic embryos, I think we should not look at mosaic embryos as the binary. They're probably somewhere in intermediate, where mosaic embryos do not mean they're completely non-viable. A proportion of them are definitely viable. But at the same time, mosaic embryos do not mean completely normal. A proportion of them are definitely abnormal. So look at mosaic state as a state of uncertainty. And this is a very important point in counseling your patients when you have to transfer mosaic embryos, that you are telling them that it is a point of uncertainty. We are not sure whether it is going to lead to a live birth or a miscarriage or failure of implantation. Your chances of implantation are low, but it is an uncertain embryo. By putting it, we are just possibly giving you a chance that there can result in a pregnancy. We should not commit on the mechanism of self-correction. And therefore, I would close with this slide where I believe that the most extraordinary property of a human embryo is perhaps not its ability to correct, but its capacity to tolerate it and ability to get off from it to result in a live birth. Thank you so much, and I'll be happy to take questions.